Hey, morning, guys. Welcome back to class. We're going to continue the column design today, precisely analysis today. We don't probably have time to finish the design problem. So in the exam, you probably only see the analysis one, okay? And I uploaded the grades yesterday from the exam two, just one day for us maybe to take a look at it. And if you want, you can also start computing your average grades by taking the homework percentage. We have one more homework on the column, and that's it. So you can probably have a good estimation of where you're at. Now, if you have any question about the grades, today is the best time to reach out to me. So just send me email so I know what's going on. If you have other things you want to discuss, like question about homeworks and future other works, you can also send me email about it. Okay. So that's about it. So let's get it right into it, the column analysis, okay? So last time we have talked about the column stress analysis, right? So in the column, there are reinforcement and there are concrete cross sections, right? So in terms of a reinforcement, I have the FYAST, which is taking care of the yield strength of the bars and the area of steel. And for the concrete part, I have F prime C, which is compressive strength multiplied by AC, which is the area of concrete, but with a reduction factor K3 in front of it. Okay, and we know that the reduction factor K3 is 0.85, 85% of the content. Okay, all right, so we also know that any question for me? All right, okay. So I also know that the behavior of the column, right? Behavior column come from the combined behaviors of the steel and concrete together, right? So for the steel, I have elastic plastic behavior, and for the concrete, I have this nonlinear behavior. So add them together, I have this nice elastic and hardening behavior, hardening behavior. So a key word, hardening, right? So just want to write that out, hardening, okay? Now, you don't have to understand the definition of it, but it means that if I have my force increases as my displacing or strain increases, that means it's a strain hardening behavior, strain hardening behavior. Vice versa, if my stress or force drops and I have a strain softening behavior. All right, so that's the definition of that. And we went on and talked about the force and bending moment origins, right? So in another word is why do we have bending moment anyway, right? So we have shown that a beam sitting on a column with an eccentricity of from the center, and we know that this will cause us a bending moment by force multiplied by distance. And then we analyze the stress state of this bending moment combined with axial force cases, and we said that because of the combined loading, I have both compressive stress from the force and the tension compression stress from the bending. So hence, I have a combined stress state, right? So the stress in the concrete can be decomposed in two parts, from axial and from bending, right? Simple as that. Now, we also talk about it, said if we want to find out the failure criterion for the case, we have to do is take out this equation, right? This is the stress of the concrete, and let it equal to a so-called critical stress FCU here, right? And then if we divide FCU on both sides of the equation, I end up with this equation right here, where this is the axial behavior and this is the bending behavior. So it's whichever reaches one first, the column will fail, right? Excuse me. So in this case, we can define a which is the area multiplied by FU, CU, which is the critical stress of the concrete, and let it be the maximum axial force the column can take. We also can define this FCU multiplied by I divided by Y as the maximum moment that the concrete can take. In this case, we can convert our equation, simply become P over P max plus M over M max equal to 1. And this is so-called the failure criterion equation, Okay, the physical meaning of that is if we draw a moment an axial force diagram, we'll see this red diamond shape of curve, and within the curve means column is safe, and outside the curve means column is not safe. It's going to fail, right? So that's the gist of interaction diagram, right? This is the gist of the interaction diagram. Okay, now we also talk about it. This diagram was based on assumption that the stress-strain relationship is linear. Stress-strain relationship is linear, it's a straight line, okay? And we can have the straight line here. But if the material's property is not linearly elastic, for example, in concrete it's non-linear, we cannot draw a diamond shape like this, okay? We cannot draw a diamond shape like this. So we talk about how the stress distribution will look like for the concrete cross-section, right? So take a look at this column right here and have the height of H and the forces right on the side. I have the bending moment to flip the section trying to see the strain, and this is my strain distribution, this is my stress, and we say, okay, now the total axial force equal to the compression force from the concrete plus the compression force from the steel, right? So that's the compression side of it. And I have Mn, which is the bending moment, and we sum the bending moment with respect to the centroid of the section, right? So I have that compression multiplied by the lever arm, which is half H, is the half of the height of the beam, minus half A, which is the center of the compression force from the concrete. And then I have the compression force of steel multiplied by the half H minus the position of the steel, which is ds prime, and plus the tension multiplied d minus H over 2, and that is the tension side of steel. Now, some of you may ask about, when you talk about Pn, that's the axial force. You only take care of the compression from the concrete and the compression from the steel. What happens to the tension of the steel? Because you do consider that in calculating the moment. It's simply because Pn equal to Cc plus Cs equal to Ts. Right? So the compression equal to tension still holds. Compression equal to tension still holds. Right? So some people may still ask about, it doesn't make sense at all. That means like the total external force, right? Pn and you have a tension Ts, they cancel each other. So what is the force anyway? Now that's not the case, right? That's the illusion because Pn is so-called external force. Is the force applied. Now, with Pn applied, you have compression, right? And you have tension because the eccentricity. So this tension here is called internal. It's called internal. So this is external equal to internal, right? That's different, right? That's different. Okay, so don't confuse yourself. All right, so we move on, said, okay, now I know the moment, I can write it out and I have the moment equation. So essentially at this point, we have a compression equation and a moment equation, compression equation and moment equation. Now look at the compression equation have 0.85 is the constant, F prime C is the constant, A is the size, B is the size, A prime S is the reinforced area and compressive reinforcement, F prime S is the stress state in the compressive reinforcement, 0.85 is known, F prime C is known, so F prime S is unknown. We don't know, right? And looking back in the moment, same thing happened. I have all these are known, all these are known, all these are known, known. So what I don't know is A, what is the compressive zone size? I don't know. And F prime S, what is the compressive stress in the bar? I don't know. And what is the stress in the tension side of the bar? I don't know, right? So the name of the game now is trying to find out what are these unknowns. What are these unknowns? Because once I can determine these parameters, right? If I can determine these parameters, I pretty much can determine the axial force and the bending moment that I can draw it. That is to say, if I start drawing my moment and axial force interaction diagram, right? So let me just write it out here. So interaction diagram. Okay, and this is actually a term, okay? So whenever people tell you interaction diagram, this is none other is axial force versus a bending moment diagram. Okay, so this is called interaction diagram. All right, so recall what I just said. If I can determine all these parameters, right, all these unknown parameters, I can basically find a point on this quadrant here, So I started thinking, what kind of points I will have on the envelope, right? So what I'm trying to do is failure envelope. Another term. What does it mean by failure envelope? It means that I'm trying to find a line that corresponding to failure, i.e., I'm trying to find a line that corresponding to failure. Corresponds to failure. That means I want to find the dots that connect the line, and these dots representing the failure state, right at the failure, right at the failure. So I started thinking about it. What point I start to see failure? What's the easiest I can do, right? So start thinking, oh, look, if I can do just compression, pure compression, that means I don't have any bending moment. I just put a force right at the center of the section, right? I will have a pure axial load. So I call this point A and a pure axial load. And this will be the first point on the diagram because I know that at this point I have, let me use a different color. You don't have to change it, but just for my own sake. So this is pure axial load. And I know that in this case, my eccentricity equal to 0. There's no off distance. And if I apply a force there to the maximum axial force, P naught, I'm going to fail it. I'm going to fail it, right? So that's the first point on the diagram. That's the first point on the diagram. It's not too bad, isn't it? It's not too bad, right? So now with this, and again, this is for my sake, I'm just going to draw it big, and you don't have to change anything. But for me, oh, sorry. For me, I just want to show a little bit clear. So let me draw it big. Yeah, so this is big enough. All right, so now I have the first point, which is axial force, right? Pure axial loading. Now, I want to see what it looks like, right? So let me just draw some small diagram underneath it. Say A equal to pure axial load. Pure axial load, right? And what it looks like is the stress. Say, take a look at the stress. It's pure axial load, right? So there's no bending, there's no tension. It's just pure uniform compression. Uniform compression, right? Looks like that. And if I take a look at the strain, take a look at the strain, it is the same, right? It is the same. So I have pure compressive strain. Pure compressive strain. Okay, so that is as simple as that. As A, that's the pure axial load. Now I start to think, right? I start to think, a very dangerous action, right? People actually think. So I start to think, if I start to apply bending moment on it, if I start apply bending moment on it, when I start apply bending moment on it, I'm just gonna start thinking maybe there's a point B, right? Point B. But before I say what is point B, I'm just gonna take a look at the stress, right? The stress, right? I started putting bending moment. I started putting bending moment on it, and as long as I start putting bending moment on it, my stress changes, right? I will have a compressive stress here, but if I have more bending moment, I have a reduction of compressive stress. Okay, and keep going till the point that I have a zero tension or zero compression, right? Zero tension or zero compression means there's no stress at the end of the section. I can achieve this point, right? I can achieve this point. And the strain diagram correspondingly looks just like the triangle. Just like the triangle, right? I mean, I don't know when, I don't know exact number, but I can do that, right? I can just apply moment and squeeze the section till that at one point on the section have zero stress, And I call this state as a point of zero tension. Point of zero tension means no tension or no compression at all. Okay, so I know since it is going to be zero tension, and at this point I have combined axial force and the moment, so the failure I cannot have as high as a compression as pure compression case. So I'm just going to slow down on this diagram and put point B here. Okay, and I call this again, let me use different color, point of zero tension. Now, some of you may argue, look, it's zero compression. Oh, I say it's the same, but we prefer tension, but because at A is pure compression, right? So now I have pure tension, right? Sorry, zero tension. Excuse me. Okay. All right, so that's my next point. That's my next point. All right, so I keep going. I keep going. I say, look, now I've passed the Rubicon, right? I passed the Rubicon, the point of no return. Now I just get the zero tension there. I keep applying moment. I keep applying moment, right? So I say, look, if I keep applying moment, right, there might be a point, right? There might be a point that in terms of strain, I can reach the compressive strain of concrete. Compressive strain of concrete. Oh, mind you that, okay, all these A and B, the compressive strain of concrete is reaching at the failure, right? That's the failure state we're talking about. Failure state we're talking about, right? So I have epsilon Cu, that's the compressive strain of the concrete, okay? And then I keep dragging it to tension side of it, keep dragging to tension side of it. And now, I reached the point where exactly my steel has the strain of yield strain. Okay, my steel has a strain of yield strain, and yield strain for grade 60, you all know that is 0 0.00207. 0.00207. Okay, so that means I can keep applying moment to at the point that my compressive strain of concrete reaches the failure, and my tensile strain of steel reaches the yield point. And I call this a balanced failure. I call this a balanced failure. Okay, so scrolling down the memory line, A and B, now I have my balanced failure somewhere right here. Okay, somewhere right here. Okay, so let me switch a color and I call this balanced failure. Okay, so that's the point C. Now, again, I can still pushing, right? I can still pushing, right? I can continue to do that, and I apply more bending moment. Now I always keep, you can see that I always keep the compressive strain of the concrete at epsilon Cu, right? So again, this is constant epsilon Cu, and apply more moment. My neutral axis shifted, right? So here, there's no neutral axis. Here, neutral axis is this almost like zero tension point is here, and for this, 0 point tension point is here, and for this, 0 point tension is going to be up a little bit more, and now I can get my strain diagram looks less like that. And I also know that my strain of steel epsilon s here will be bigger than the yield strain, and now happen to be 0.005. Happen to be 0.005. All right, and now I call this a tension controlled failure. Or I don't call it, people call it already, right? But this is defined as tension controlled limit. Tension controlled limit. Okay, you probably know that already, right? Remember how we determine phi, the strength reduction factor for this case is 0.9, right? For this case is 0.9. So now I have my point D. Now where it is, right? Is it going to be on the right side of C or is it going to be the left side of C? Which one, right? So I started thinking. At the point of C, my steel already reaches the yielding strain. Okay, that means my stress in the steel in tension side equal to the yield stress, right? Now, on the right-hand side, since I have a higher strain, so steel also have the strength of the yield strength. So they look the same, but take a look at the compressive zone size, right? So compressive zone size, sorry, this is not A, this is C. Compressive zone size for point C is much bigger than compressive zone size for point D, right? That means D has a lower moment, So naturally, I'm gonna put my point D right here on the left-hand side of it. Okay, point D on the left-hand side of it. And let me just put a name on it. This is called tension controlled limit. Tension controlled limit. Okay, all right. So this is the next point. Now, some of you say, okay, look, Bob, you're done, right? I mean, you have all the points, right? What else are you gonna go? And you keep going. If you keep going, apply more, apply more bending moments, you're going to end up with the same scenario as D, but the strain just go on and on and on and on and on. So what's the point of that? What's the point of that? Yes, there is a point, and I'm going to show you why, right? So if I if I apply more bending moment, okay, I will reach the final stage of E, okay? At the final stage, my compressive strain concrete is still epsilon Cu, but my compressive zone size is so small, compressive zone size so small, okay? So small that my epsilon S equal to almost the breaking strain of the steel, the breaking strain of the steel. And say if this is my compressive zone size C, and this is my depth D, my C over D ratio is so ridiculously small, or C is much smaller than D. Okay, that means if I take a look at the cross section, this is a cross section, and this is my neutral axis or center line here. My axial force is so down here, and my eccentricity is almost infinity. Okay, almost infinity. All right. At this point, I have the maximum bending moment somewhere here. Okay, that means I cannot have any compression at all because I have such a small compressive zone for the concrete. So there's almost no concrete that take care of the compression. All right, and I call this a small compressive zone state. Small compressive zone state. All right, so now I can write it out here, say this is small compressive zone. Sorry, small compressive zone. All right, and I just want you to mind that this is E eccentricity equal to infinity. All right, so here epsilon S equal to 0.005. Here epsilon S equal to 0.0027. And here I would say that F concrete at the bottom here equal to 0. And here it's equal to 0. Okay, so these are the criteria for this point. These are the criteria for this point. Okay, okay. All right, so if this is still hard for you to remember, right? This is still hard for you to remember. I draw a mini diagram here. I can draw a mini diagram here. I call this A, B, C, D, E, alphabet song, right? So alphabet song goes like this. It is originally a rectangular shape in terms of strain. And then I jump to a triangle, my triangle getting bigger, and my triangle getting even bigger, and my triangle completes into a reverse triangle. Okay, so that is what's going on as I increase the moment. Okay, as I increase the moment. All right, so now you know why we have picked this point, why we have picked these points. Now, with these points are defined, I can connect these points, and they look just like this. They look just me in a bar on a Friday night, and so full of beer, right? I have a belly right here, and my belly button is point C. Okay, so this is the interaction diagram. This is the interaction diagram. Okay, now we have the interaction diagram, but it's not yet complete because I want to divide these interaction regions into zones. Okay, so I start observing it. I say, look, if I connect a straight line, here from 0 point to C, okay, from 0 point to C, and in this region here, okay, region A to C, okay, this is a compressive failure. Why? Because my steel is just before yielding, right? Hasn't reached the yielding state. So this is a compression failure. And mind you that phi equal to 0.65, remember? Phi equal to 0.65, right? Right. And now, if I draw another line connecting Z0 to D, And this region from C to D, right? And this is actually the transition zone, remember? Because it's all about strain in the steel. And this because the strain is between 0.00207 to about 0.005. So this is a transition zone. And now if I look at D to E, and this is so-called tension controlled failure, right? Tension controlled. And phi equal to 0.9, remember? Phi to 0.9. Okay, all right, so now we're complete. Now we're complete. And this is the interaction diagram. Okay, so that means if I give you a column, give you a reinforcement and cross-section detail, you should be able to draw this interaction diagram by finding these points A, B, C, D, E first, then connect them to the line showing here. All right, so this is the conceptual part of it. I just want to pause here and welcome any questions from you guys. Any questions? Any questions on the concept? Are we good on this? Okay. All right. So this is not too hard to comprehend, right? This is just a simple moment force and moment diagram, right? Force moment diagram. So with this, right? I want you to take a look at an example, right? I want you to take a look at an example. Okay. So now let's take a look at an example, right? Example. Let me use blue color. So, right? Given the column below, okay, and we want you to determine the following. But let me show the column, right? So the column looks just like this. It has a height of 20 inches, h equal to 20, and have a width of 12 inch. Okay, and my axial forces, right? My axial forces is sitting somewhere here. It has this distance of eccentricity of this much. Okay, you notice that I put a sign of cross means the force is going into the plane, Okay, and for the reinforcement detail, I have 4 number 9 bars. Okay, matter of fact, let me move the sign here in the center. That you don't have to, but I'm just want to put it here because it looks more legit. I don't want to create like another bending moment the other direction. Okay, so I have 4 number 9 bars, and I have stirrups going around it. Hoop stirrups going around it, like so. Okay, and my distance of the top bar from the top concrete is 2.5 inch. Distance from the bottom bar, so the bottom side of the concrete is 2.5 inches as well. Okay, so this is the cross section, right? So let's determine first the axial force and moment. Axial force and moment correspond to balance failure, corresponding to balance failure. Okay, I just want to be clear. This means actually point C. Okay, point C. All right, now the second is the axial force and bending moment. Axial force and bending moment to represent intention failure region. Means I need to pick a point, right? Intention failure. So take a look at the diagram. Tension failure, right? What is the tension failure? Tension failure means D to E, right? D to E. So somewhere D to E. Okay. And number 3, axial force and bending moment. Okay. 4, representing point in compression failure. Compression failure. region. That is actually A to B. Okay, and number 4 is the axial force for, actually there's no moment now because this is for pure axial load. Okay, and this means I want to find out the point that eccentricity equal to 0, and this is point A. Okay, essentially the point A. And I gave the materials property to you, and now the concrete compressive strength at prime C equal to a 4,000 psi. Okay, and the yield strength of the bar equal to 60 ksi. Okay, so this is all we know. This is all we know. All right, so we need to find out these points. We need to find out these points. Now, first thing first, right? Let me draw the section again. So I have this section right here. And let me just omit the stirrups and only leave the number 9 bars at the corners. Okay. And now, if these are number 9 bars and I want to put the strain diagram here, so this is my strain diagram. Remember, I start and always maintain the compressive strain in the concrete on the edge equal to 0.003. And I have a compressive strain for steel equal to epsilon s prime. I have a compressive zone size of C. And I have a tensile strain on the steel epsilon s. Right, so this is my strain diagram. So in terms of stress, I can draw the Whitney stress block. This is the compressive stress from the concrete, and the width is 0.85 F prime C. Okay, and I have a compressive force from the steel, which is AS prime, FS prime, and I have a tension force here, AS, FS. And now this is A. Okay, in terms of internal forces, I have CS prime, I have CC, I have tension TS. Okay, so strain, stress, and internal forces. Okay, so these are my diagram. These are my diagram, right? And I want to find these points. I want to find these points. So before I do anything, I just want to draw it here and give myself a hint what points I need to find first, right? So I need to find A. I need to find something between them. So I need to have B, C, D, E. Okay, so I need to find the points here. I need to find the points here. Okay, so first thing first, right? Number 1, to find point C, the balance failure, So at balance, right, I want to take a look at the strain diagram. I know that my compressive strain for the concrete at balance reaches epsilon Cu equal to 0.003. Now the steel, on the other hand side, reaches the yield strain, which is epsilon s equal to epsilon y equal to 0.00207. Why I know this? Because it's grade 60. And now I just need to find out the compressive zone C and then determine my Fs prime, which is the stress in the steel. But to know that, right, I need to have epsilon s prime, which is the compressive strain of the steel. And the distance between the top fiber and the compressive steel is ds prime. ds prime. All right, and knowing that the depth of the bar is d here, depth of bar d here. Okay, so these are the strain distribution. I can start computing, right, to get my compressive zone size. So first of all, my epsilon Cu equal to 0.003. Epsilon s equals to epsilon y equal to 0.00207. Okay, and now C, compressive zone size, equal to a D multiply epsilon Cu divided by epsilon Cu plus epsilon s, and that is 17.5 inch. D is 17.5 inch, by the way, and multiply 0.003 divided by 0.003 plus 0.00207. Okay, and I get my C equal to a 10.3 inches. That's the compressive zone size. Now A, which is the effective one, equal to beta 1 C, and that is 0.85 multiplied by 10.3 inches, and I have A equal to 8.76 inches, right? And now the stress in tension Fs equal to Fy, because yield, and Fs prime equal to Es multiplied by epsilon S prime. And now I can compute the Fs tension side of stress equal to Fy, so 60 KSI. Okay, now Fs prime, this fellow here, Es, right, which is the Young's modulus of the concrete, so still right here, Es. Now this is the compressive strain of the steel, and that actually equal to epsilon Cu multiplied by C minus ds prime divided by C, okay, from the triangle, right, trigonometry. And then bring the number in, so this is 29, sorry, this is steel, okay? This is steel, 29,000 KSI, if Young's modulus, right? Multiplied by, bracket inside 0.003, multiplied by here, this is 10.3 minus 2.5 divided by 10.3 again, okay? And now I have a 65.9 KSI. Now, when you see this number, alarms start going, right? Because this is bigger than the yield strength of the steel. Okay, but this is okay. This is okay. We can just say in compression in column, okay? This is only in column, right? So in column, we can use Fs prime equal to Fy equal to 60 KSI. Why is that? Because in column design, okay, we allow compressive reinforcement to yield. So it's different from the beam, okay? In column, you allow compressive reinforcement to yield. It's okay, you can allow to yield. All right, so now that is the compressive stress in the steel for this point. Okay, so now I have to take a look at the compression force. So for the compression force, I have concrete CC, which is equal to 0.85 F prime C, 0.85 F prime C A, B, and 0.85 right in front of it. And F prime C is 4 KSI, and A is 8.76 inches. Okay, where did I get that from? This is where I did get it from, right? A equal to 8.76 inches, and then B is 12 inch. So I plug the number, I have 357 kips, and that is the compression force from the concrete. Okay, compression force from the concrete. All right, so this is the compression force from the concrete. I want to find a steel, so CS prime equal to AS prime multiplied by FS prime minus 0.85 F prime C. You should see this equation from W reinforced section, okay? Now AS prime, I have two number 9 bars at the top, so 2 inch squared, okay? I have a yield strength of 60 KSI for the compressive bar, and remember, because it capped there, and minus 0.85 multiplied by 4 KSI, and I got this number to be 113.2 kips. 113.2 kips, and that is the compression force for the steel. Okay, now I have basically the TS tension side equal to ASFY. Okay, and that is 2 inch squared. Okay, multiplied by 60 KSI, and I have 110 KSI. Sorry, 110 kips. 120. Sorry, 120 kips. That is the yield strength. That is yield strength. Okay. All right. Okay, so let's examine the cross section. Let's examine the cross section, right? So now I have the, let me just draw that out, okay? I have the cross section here. Okay, I want to make a cut somewhere here. I want to make a cut. So once I made a cut, right? I have the top section like this, and I have the cut right here. have the cut right here. Okay, so I want to do a free body diagram to show what is my compression forces and what is the bending moment and all that, right? So first of all, I want to show the one side of the story. So here is my P axial force, and this is the center line. So the distance here is E. Distance here is E. Okay, so this is on the top surface, nothing else, right? This is on the top surface. So if I made a cut somewhere here, I start taking a look at the section, right? I start taking a look at the section. Let me use a different color here. So now this is along the line here. So here I have C, sorry. Here I have C, and I also have CS prime, and I have TS. All right, so that is the bottom surface. That is the bottom surface. Okay, so now if I want to make a balance, I say this is Z, this is Y, this is X. I want to make a balance, right? So first thing first, I need to sum the force in the Z direction, right? Sum the force in Z direction. So P equal to CC plus CS prime minus TS. Okay, pay attention, it's a bit different, okay? A little bit different. I'm trying to do a free body diagram here, okay? And now you can see this is the equilibrium in Z direction, right? Now I have Fx direction equal to 0 because there's no force in the X direction, and Fy action 0. There's no force in the Y direction, okay? Now I want to sum the moments. And notice that I only have moment in terms of X direction, Okay, so on the left-hand side, I have P multiplied by E, which is the moment. I don't know exactly how much, but that is the moment. And the right-hand side, I have the moment. I'm going to use the previous equation, right? CC, compression, multiplied by half H minus half A. Okay, plus CS prime, which is the compression force from the steel, multiplied by half H minus D prime. And plus tension side of it, and D depth minus half H. So now that is the moment from right-hand side. Okay, so given all this, I can start computing. So I get my total force P here equal to CC plus CS minus TS. So I have 357 plus 113.2 minus 120. I have a 350.2 kips as my total compression force. And my moment equal to this whole thing, right? So I'm just going to say this whole thing. Okay. And then equal to 357 kips multiplied distance is 10 inches minus 4.38 inches. You can check on these numbers, okay? And plus a CS prime, which is 113.2 kips, and multiplied distance of 10 inches minus 2.5 inches, and plus a 120 kips tension side of it, and multiply 17.5 inch minus 10 inches. Okay, and the whole thing in terms kips inch, so I need to divide by 12 inch per foot to convert back to foot, and have this number to be 310 kips foot. All right, so now I have the moment, I have the force. I need to find eccentricity. So eccentricity E equal to moment divided by force. So 310 kip foot divided by force, which is 350.2 kips, and let's multiply 12 inch per foot to convert back to inches, and I have a 10.66 inch, and that is the eccentricity I have. Okay, so at this point, I have point A, point C, which is the balanced failure, and I have axial force of 350.2 kips. I have moment, which is 310 kip foot, and I have eccentricity of 10.66 6-inch. Okay, to mark it on my curve here, this is essentially C, and I can write down P equal to 350.2 kips, M equal to 310 kip foot, and eccentricity equal to 10.66 inches. Okay, all right, I think this is a good point to stop. Okay, so we just finished part 1, essentially to find the balance failure. Okay, all right, so you may want to take a little bit of time to digest because this is a lot of information for the first time column analysis, and we can continue tomorrow at 1 o'clock. Okay, all right, so let me stop here, and you're welcome to stay for any questions, and we can discuss if you have other things as well. Okay.